Artificial Intelligence Part 2 is working on classical human imitative AI the best or only way to focus on these larger challenges. Some of the most heralded recent success stories of ML have in fact been in areas associated with human imitative AI, areas such as computer vision, speech recognition, game playing and robotics. So perhaps we should simply await further progress in domains such as these. There are 2 points to make here. First, although one would not know it from reading the newspapers, success in human imitative AI has in fact been limited. We are very far from realizing human imitative AI aspirations. Unfortunately, the thrill and fear of making even limited progress on human imitative AI gives rise to levels of over-exuberance and media attention that is not present in other areas of engineering. Second, and more importantly, success in these domains is neither sufficient nor necessary to solve important IA-N2 problems. On the sufficiency side, consider self-driving cars. For such technology to be realized, a range of engineering problems will need to be solved that may have little relationship to human competencies or human lack of competencies. The overall transportation system N2 system will likely more closely resemble the current air traffic control system than the current collection of loosely coupled, forward-facing, inattentive human drivers. It will be vastly more complex than the current air traffic control system, specifically in its use of massive amounts of data and adaptive statistical modeling to inform fine-grained decisions. It is those challenges that need to be in the forefront, and in such an effort a focus on human imitative AI may be a distraction. As for the necessity argument, it is sometimes argued that the human imitative AI aspiration subsumes IA-N2 aspirations, because a human imitative AI system would not only be able to solve the classical problems of AI as embodied, e.g., in the Turing test, but it would also be our best bet for solving IA-N2 problems. Such an argument has little historical precedent. Did civil engineering develop by envisaging the creation of an artificial carpenter or bricklayer? Should chemical engineering have been framed in terms of creating an artificial chemist? Even more polemically, if our goal was to build chemical factories, should we have first created an artificial chemist who would have then worked out how to build a chemical factory? A related argument is that human intelligence is the only kind of intelligence that we know, and that we should aim to mimic it as a first step. But humans are in fact not very good at some kinds of reasoning. We have our lapses, biases and limitations. Moreover, critically, we did not evolve to perform the kinds of large-scale decision-making that modern two systems must face, nor to cope with the kinds of uncertainty that arise in two contexts. One could argue that an AI system would not only imitate human intelligence, but also correct it, and would also scale to arbitrarily large problems. But we are now in the realm of science fiction. Such speculative arguments, while entertaining in the setting of fiction, should not be our principal strategy going forward in the face of the critical IA-N2 problems that are beginning to emerge. We need to solve IA-N2 problems on their own merits, not as a mere corollary to a human imitative AI agenda. It is not hard to pinpoint algorithmic and infrastructure challenges in two systems that are not central themes in human imitative AI research. Two systems require the ability to manage distributed repositories of knowledge that are rapidly changing and are likely to be globally incoherent. Such systems must cope with cloud-edge interactions in making timely, distributed decisions, and they must deal with long-tail phenomena whereby there is lots of data on some individuals and little data on most individuals. They must address the difficulties of sharing data across administrative and competitive boundaries. Finally, and of particular importance, two systems must bring economic ideas such as incentives and pricing into the realm of the statistical and computational infrastructures that link humans to each other and to valued goods. Such two systems can be viewed as not merely providing a service, but as creating markets. There are domains such as music, literature and journalism that are crying out for the emergence of such markets, where data analysis links producers and consumers. And this must all be done within the context of evolving societal, ethical and legal norms. Of course, classical human imitative AI problems remain of great interest as well. However, the current focus on doing AI research via the gathering of data, the deployment of deep learning infrastructure, and the demonstration of systems that mimic certain narrowly defined human skills, with little in the way of emerging explanatory principles, tends to deflect attention from major open problems in classical AI. These problems include the need to bring meaning and reasoning into systems that perform natural language processing, the need to infer and represent causality, the need to develop computationally tractable representations of uncertainty, and the need to develop systems that formulate and pursue long-term goals. These are classical goals in human imitative AI, but in the current hubbub over the AI revolution, it is easy to forget that they are not yet solved. IA will also remain quite essential, because for the foreseeable future, computers will not be able to match humans in their ability to reason abstractly about real-world situations. We will need well-thought-out interactions of humans and computers to solve our most pressing problems. And we will want computers to trigger new levels of human creativity, not replace human creativity, whatever that might mean. It was John McCarthy, while a professor at Dartmouth, and soon to take a position at MIT, who coined the term AI, apparently to distinguish his budding research agenda from that of Norbert Wiener, then an older professor at MIT. Wiener had coined cybernetics to refer to his own vision of intelligent systems, a vision that was closely tied to operations research, statistics, pattern recognition, information theory and control theory. McCarthy, on the other hand, emphasized the ties to logic. In an interesting reversal, it is Wiener's intellectual agenda that has come to dominate in the current era, under the banner of McCarthy's terminology. This state of affairs is surely, however, only temporary. The pendulum swings more in AI than in most fields. But we need to move beyond the particular historical perspectives of McCarthy and Wiener. We need to realize that the current public dialogue on AI, which focuses on a narrow subset of industry and a narrow subset of academia, risks blinding us to the challenges and opportunities that are presented by the full scope of AI, IA and II. This scope is less about the realization of science fiction dreams or nightmares of superhuman machines, and more about the need for humans to understand and shape technology as it becomes ever more present and influential in their daily lives. Moreover, in this understanding and shaping there is a need for a diverse set of voices from all walks of life, not merely a dialogue among the technologically attuned. Focusing narrowly on human imitative AI prevents an appropriately wide range of voices from being heard. While industry will continue to drive many developments, academia will also continue to play an essential role, not only in providing some of the most innovative technical ideas, but also in bringing researchers from the computational and statistical disciplines together with researchers from other disciplines whose contributions and perspectives are sorely needed, notably the social sciences, the cognitive sciences and the humanities. On the other hand, while the humanities and the sciences are essential as we go forward, we should also not pretend that we are talking about something other than an engineering effort of unprecedented scale and scope. Society is aiming to build new kinds of artifacts. These artifacts should be built to work as claimed. We do not want to build systems that help us with medical treatments, transportation options and commercial opportunities to find out after the fact that these systems don't really work, that they make errors that take their toll in terms of human lives and happiness. In this regard, as I have emphasized, there is an engineering discipline yet to emerge for the data-focused and learning-focused fields. As exciting as these latter fields appear to be, they cannot yet be viewed as constituting an engineering discipline. Moreover, we should embrace the fact that what we are witnessing is the creation of a new branch of engineering. The term engineering is often invoked in a narrow sense, in academia and beyond, with overtones of cold, affectless machinery, and negative connotations of loss of control by humans. But an engineering discipline can be what we want it to be. In the current era, we have a real opportunity to conceive of something historically new, a human-centric engineering discipline. I will resist giving this emerging discipline a name, but if the acronym AI continues to be used as placeholder nomenclature going forward, let's be aware of the very real limitations of this placeholder. Let's broaden our scope, tone down the hype, and recognize the serious challenges ahead. Thanks for watching.